Order of reaction. Zero order. This is the rate law for zero order. Rate is equal to K to the concentration of reactant A to the power of 0. Any value to the power of 0 is equal to 1. 1 times K is equal to K. Thus, rate is equal to K for zero order. From this rate law, we know that rate is not dependent on the concentration of the reactant because rate is equal to K. There is no concentration of reactant at all in the rate law for zero order. Know that rate is equal to K for zero order and rate equal to negative dA over dt. So K is equal to negative dA over dt. For integrated rate law, integrate the rate law, the concentration of reactant A initially means the initial concentration of reactant A minus the concentration of reactant A at a particular time equal to KT. You can rearrange this equation. AT, the concentration of reactant A at a particular time, equal to the initial concentration of reactant A minus KT. So you can find the concentration of the reactant at a particular time if you have the initial concentration of reactant A, the time, and the rate constant. So this is integrated rate law for zero order. For zero order graph, on the y-axis you have the rate of reaction, on the x-axis the concentration of reactant A. So we know that rate law for zero order, rate is equal to K. So rate of reaction for zero order does not depend on the concentration of reactant. So this is the zero order graph because the rate does not depend on the concentration of reactant A. There's no relationship between rate of reaction and the concentration of reactant for zero order reaction. For integrated rate law, for equation, reactant A concentration at a particular time equal to the initial concentration of A minus KT. So this is a graph for reactant A concentration on the y-axis and the time on the x-axis. So the initial concentration decrease against time. So this is initial concentration, and then the concentration of A decrease over the time. For the second enrollment, initial concentration minus concentration of A at particular time equal KT. This is a graph when the initial concentration of reactant A minus the concentration of reactant A at particular time against T on the x-axis. So it will increase. Zero order half-life. From integrated rate law, we know that the concentration of reactant A at particular time minus the initial concentration of reactant A is equal to negative KT. The half-life is equal to T when the concentration of a reactant A at particular time equal to initial concentration over 2, because we know that half-life, the concentration becomes half from the initial concentration. So that's why initial concentration over 2 means it becomes half. So that's the half-life. So when AT is equal to A0 over 2, substitute into AT. So A0 over 2 minus A0 equal negative KT half. So this T is half-life. So substitute this T equal to half-life. then rearrange the equation. Negative A0 over 2 equal negative KT half, and then the half-life equal A0 over 2K. This is the zero-order half-life equation. This is how we get the zero-order half-life equation from integrated rate law. And then substitute AT equal A0 over 2. Rearrange the equation. You'll get the equation of half-life. A0 means the initial concentration of reactant A over 2K. From this zero-order half-life, we know that half-life is directly proportional to the initial concentration of reactant A. This is the graph. So the first one, before the reaction start, we have the reactant A, initial concentration of reactant A, and then divide by 2 when the concentration of reactant A becomes half. That's our half-life, the first half-life. It becomes half of concentration initial of reactant A, and then the second half-life is half of 1 over 2, which is 1 over 4. This is the second half-life. So the half-life is directly proportional to A0. You can see from this graph, it's directly proportional to A0 from the equation of half-life. First order, rate equal Ka to the power of 1. That is the first order. This is the rate law for first order. Rate equal Ka. A is a reactant. Power 1, but we don't write 1 understood as 1 here. Rate is directly proportional to the concentration of reactant. We have here rate equal K, concentration of reactant A. So means it is directly proportional. If the concentration of reactant A is double, the rate is double. If you double this concentration, the rate will be double. So it will become 2A. So rate equal K to A. If you double the concentration of reactant A, the rate will be double. And then it will become rate equal 2K concentration of A. Example of the first order reaction is radioactive reaction or radioactive decay rates. So if you encounter any question of radioactive reaction and it doesn't state the order of reaction, you have to understand that that is the first order, because radioactive reaction undergoes first order reaction, or any decay reaction, first order reaction. So this is the rate of first order, rate equal Ka. The rate law, rate equal K times concentration of reactant A, and then rate equal negative dA over dt, Ka equal negative dA over dt. This is what we get from the rate law. From integrated rate law, we have ln concentration of reactant A initial minus ln concentration of reactant A at particular time equal Kt. When we integrate the rate law, you got this equation, and then rearrange the equation. Ln At equal ln A0 minus Kt, and rearrange this equation. Ln A0 over At equal Kt. This is the integrated rate law for the first order. First order graph, we know that rate equal to Ka, and we know from this rate law, we know that the rate is directly proportional to the concentration of the reactant. So as the reactant concentration increase, the rate of reaction increase. Integrated rate law first order graph, for ln A0 over At equal Kt, the y-axis is ln N0 over concentration of reactant A against T, and then this is the graph for ln AT equal ln A naught minus KT. On the y-axis, this is ln A at particular time, ln A on the y-axis, and then time on the x-axis. This is the graph for the second Roman integrated rate law equation. First order half-life from integrated rate law. So here we have first order integrated rate law that you got from here, integrated rate law, ln A naught over AT equal KT. So this T, we want to find the half-life, so this T must be T half, the half-life. T half is when AT equal A naught over 2, means the concentration of reactant A equal to the concentration of reactant A initial over 2, half of initial concentration, that is AT for half-life. So substitute this into AT, and then T replace with T half, and you will get the half-life for the first order is equal to ln 2 over K. This is the equation for first order half-life. As you can see here, the half-life does not depend on the initial concentration of reactant at all. There's no A naught here, it's just ln 2 over K. So half-life does not depend on the concentration of the reactant initial concentration. So this is the graph. Initial concentration becomes half, 1 over 2, it becomes half. That's the first half-life. And then half of 1 over 2 is 1 over 4 initial concentration. That's the second half-life. This is the graph for the first order half-life. First half-life is equal to second half-life. Thus, T half, the first one equal T half for the second one. That's the first order half-life. Second order rate law, rate equal K concentration of reactant A square. The power is 2 because second order. From here, you can see that rate is directly proportional to the square of the concentration of the reactant. For first order, it's just rate is directly proportional to the concentration of reactant. But for second order, this is power 2, it's directly proportional to the square of the concentration of the reactant. So if you double the A, the rate will be quadruple, because this is square. Double, quadruple, because 2 to the power of 2 is 4. So that's why rate quadruples. So rate equal K2A. Here you double the rate, 2A, and then this is power 2. That's why you say that the rate is quadruple. Rate equal 4KA square. Rate law, rate equal KA square, and rate is also equal negative dA over dt. So KA square equal negative dA over dt. For integrated rate law of second order, 1 over AT equal KT plus 1 over A naught. This is initial concentration of reactant A. And rearrange the equation. This is the integrated rate law for the second order. 1 over AT minus 1 over A naught equal KT. This is the second order graph. On the y-axis, we have rate of reaction. On the x-axis, make sure it's concentration of reactant A square. It's directly proportional. For integrated rate law, 1 over AT equal KT plus 1 over A naught. On the y-axis, 1 over A, concentration of reactant A, and on the x-axis time. And then this is a graph for this equation. And for this equation, on the y-axis, you have 1 over A concentration of the reactant A minus 1 over concentration of reactant A initial concentration of reactant A. So on the x-axis we have time, and then it increase. This is the integrated rate law graph for second order. Second order half-life from integrated rate law, this equation that you get from the previous slide, 1 over AT minus 1 over A naught equal KT. And then if we want to determine the half-life, have to change this T, change to T half. When change it to T half, this AT must equal to A naught over 2, half of the initial concentration of reactant A. And then substitute this into AT, you'll get the half-life equal 1 over K A naught. So from this equation, the half-life of second order equation, you know that T half is inversely proportional to A naught. Look at here, it's inversely proportional to T half. As reaction proceeds, T half increases. Because this concentration will decrease, so T half will increase as reaction proceeds. This is a second order reaction. Initial concentration of reactant A becomes half, so that's the first half-life, and half of the 1 over 2 A naught is 1 over 4 A naught. So you can see here it's double. T half second is double of the T half first. That's the second order. For the first order, first half-life equal to second half-life. But for the second order, second half-life is double of the first half-life. This is second order reaction. That's how you determine the order of reaction, by looking at the half-life. Example, a reaction starts with an initial concentration of reactant 1 molar and has a rate constant 1.65 times 10 to the power of negative 5 molar per second. So this is the value of K, rate constant, given initial concentration 1 molar. So this is concentration initial, or A naught. This is A naught, initial concentration, and this is K. What is the concentration of reactant after 100 minutes? Given time 100 minutes, but this, if you look at this rate constant, it is in second. So you have to change this minute into second first. And from this K value, you can determine the order of reaction by looking at the value. Molar per second is zero order reaction. So when you know that this is zero order reaction, you can use the zero order reaction equation. This is the zero order equation. AT concentration minus concentration A naught equal negative KT. So our T 100 minute change to second first because the constant is in second. So 100 minute is equal to 6,000 second. We don't have AT, we need to find out the concentration. We need to find out the value of AT because what is the concentration after 100 minutes? So this is a concentration at particular time, the concentration that we need to determine. AT equal negative KT plus concentration A naught. We have the value of K, 1.65 times 10 to the power of negative 5 molar per second. And we have T, 6,000 second. We have the initial concentration of the reactant, 1 molar. So just substitute everything into this equation and you will get the concentration of AT equal 0.901 molar. This is the concentration of the reactant after 100 minutes. Next example, we have the chemical equation of the reactant A becomes product. Determine the half-life of substance A if the rate constant is 0.00624 molar per second, this is K, and its original concentration is 1.2 m, this is A naught. Initial concentration, this is initial concentration, this is A naught, this is K. We need to determine the half-life, so you need to find T half. In order to choose the T half equation or the half-life equation, you need to know the order of reaction first. How to identify the order of reaction? By looking at the K unit. When the unit of K is molar per second, this is the zero order reaction. Zero order reaction, so use the half-life equation for zero order. This is half-life equation for zero order. T half equal A naught over 2K. We have the value of K and we have the initial concentration 1.2. Just substitute K and initial concentration, and the half-life of this reaction equal 96.15 seconds. Make sure you write the unit second because the K unit is in second. If it's in minute, here is minute. Depends on the K unit. Next example, the rate constant of the reaction 2A reactant becomes B product is 51 per molar per minute. So this is K value. From the K unit, you can know the order of reaction. This is the K unit per molar per minute at 25 degrees Celsius. Starting with concentration of reactant A 0.0092 molar, this is A naught, initial concentration of A. How long will it take for the concentration of A becomes 3.7 times 10 to the power of negative 3 molar? This is AT. You have A naught, you have AT. You need to find T. How long? We need to find the time taken. So, this reaction is second order because per molar per minute. Per molar per minute is second order. When the unit of K is per molar per minute or per molar per second or per molar per day, per molar per hour, it depends. You can change this. Per molar per minute, it is second order reaction. When it is second order reaction, you have to use the second order equation to find the T here. So this is second order equation. Integrated rate law of second order. 1 over AT equal 1 over A naught plus KT. Here we have the initial concentration of reactant A equals 0.0092 molar. Starting with means initial concentration, and after that particular time that we need to find out, the concentration of reactant A will become 3.7 times 10 to the power of negative 3 molar. We need to find T, so substitute these two values into the second order equation integrated rate law. And then you can get T, because we have K as well, so we can get T equal 3.168 minute. The T unit must be in minute because it follows the K unit. K per molar per minute, so the T must be in minute. B, calculate the half-life of the reaction. So this is second order reaction. Use the half-life for second order reaction equation. For second order reaction equation, half-life T half equal 1 over K A naught. We have A naught 0.0092 molar. Just substitute in there and then substitute the value of K and you'll get the half-life is equal to 2.131 minute.